Hello guys, Assalamu alaikum. I am Kashif Ali Sehgal and I'm A-levels chemistry teacher in different schools of Lahore, such as Lahore Grammar School, Lakas, Beacon House City, Roots, and I am ex-Edison teacher as well. We will be learning A-levels chemistry and I will be posting different lectures related to the A levels and AS level course. Today we will be studying organic chemistry topic halogeno alkanes or called halogen derivatives. This is a topic of AS level chemistry, but it is not limited to AS course. Of course, it is also included in A levels. When you're doing A levels, you have to revise the whole topic again. This topic covers the following subtopics. First is introduction to halogen alkanes, in which we will study that there are three types of halogen alkanes: primary, secondary, and tertiary. Then we will study about the reactions and chemical properties and physical properties of halogen alkanes. After that, finally, we will study about the uses of halogen alkanes. So starting with introduction to halogen alkanes. So what are halogen alkanes? Actually, they are derivatives of hydrocarbons in which hydrogen atoms bonded with carbon atoms are displaced or replaced by halogen atoms. One or more halogen atoms can be displaced, can be replaced against hydrogen, and we will get halogeno alkanes. We also call them alkyl halides. So halogeno alkanes and alkyl halides are one and the same thing, they are synonymous. What are halogens? You know that they are the elements of group number 17 containing fluorine, chlorine, bromine and iodine. So any one of these atoms can be put in place of hydrogen by the reaction of nucleophilic substitution, free radical substitutions or addition reactions of alkenes, such as electrophilic addition reactions. So the types of halogen alkanes are primary, secondary, and tertiary. Primary halogen alkanes are also denoted as 1 degree, secondary as 2nd degree, and tertiary as 3rd degree. Primary halogen alkanes are always one halose, one chloro, one bromo, or one iodo, one fluoro as well. So halogens, when bonded to the terminal carbon atom at the last carbon atom, or you can call it a first carbon atom, on the end of the chain, then that halogeno alkane will always be primary. And the easiest way to recognize is that the carbon atom bonded to halogen is bonded to two H's and one carbon chain. So you can say chloromethane, one chloroethane, one chloropropane, one chlorobutane, one bromo propane, one iodopropane. All of them are primary haloalkanes. Secondary or 2 degree haloalkanes have halogen atoms in between the chain, starting from 2 to anything like 3, 4, 5, depending on the carbon chain, but it will not never be terminal. So you can call it as, if you have propane, so it can be 2 chloropropane, or if it's butane, you can call it as 2 bromobutane or 2 iodobutane. So it cannot be one halogen in between the chain on the middle carbon atoms. That is called a secondary halogeno alkane. So you have seen that easy to recognize is that carbon atom that is bonded to halogen atom is bonded with one H and two R groups. Then tertiary halogeno alkanes have all three carbon atoms are there bonded with the carbon atom which is bonded to directly with halogen. So in this case we can recognize it as that the halogen is also in the middle of the chain, but on the carbon atom where halogen is placed, it also has a branch on it. So the same carbon has a halogen atom and the same carbon has a branch on it. For example, 2-methyl and 2-chloro. Chloro is also bonded to 2 carbon and methyl is also bonded to 2 carbon, but the naming sequence will tell us that we have to go for alphabetical order, so we will place 2-chloro, 2-methyl propane. So second carbon has halogen and also an alkyl group. So in this case we have a tertiary carbon, tertiary haloalkane, and you can easily recognize that because the halogen which is bonded with carbon atom, then this carbon atom is bonded with 3 carbon atoms, 3 carbon chains and no hydrogen. So this is from primary, secondary and tertiary halogen alkanes. So you can see that the first example is chloropropane, this is primary. Second example is 2-bromopropane, this is secondary. And 1,3-dichloro diiodo butane is of course a primary type of halogen alkane. So the properties of halogenalkanes, first is their melting points increases as the number of carbon chain increases. So methyl, chloromethane, bromomethane has the lowest melting point and boiling point. If you compare it with chloroethane or chloropropane, 1-chloropropane, or so the melting point and boiling point gradually increases due to the increase in the chain size as well as the increase in the van der Waals forces, and therefore the resulting in the strength of the forces to become stronger and increasing the boiling point. If we compare primary to secondary and secondary to tertiary, primary halogens have higher boiling points because they have a straight chain, and due to the straight chain and greater surface area, they have higher boiling point. Due to greater contact points, they have stronger van der Waals forces compared to secondary, and then secondary compared to tertiary. Tertiary halogen alkanes are even smaller, they have more compact structure, they have less surface area. So tertiary halogen alkanes have the lowest boiling point, secondary has higher, and primary has the highest boiling point. So solubility of halogenoalkanes, as we see that halogenoalkanes are insoluble in water, but they are more soluble in organic solvents. That makes us to allow us to separate them or to extract the halogenoalkanes from their aqueous solution into an organic solvent such as hexane, carbon tetrachloride or benzene. So you can easily extract halogenoalkanes from their aqueous solution into the organic solvent because their interaction with water is very low. They are not readily soluble, and that is again controlled by the energetics. You know the amount of energy required to break the bonds and then the amount of energy released to form the bonds. So halogenalkanes release more energy while forming interactive forces, intermolecular forces with organic solvent. Therefore, they are more soluble in organic solvent compared to with water. Uh, Organic solvents can be used to extract halogen alkanes from aqueous solution. Extraction is the process. This process is called solvent extraction, and it is quite valuable when you will study in A2. Reactions of halogen alkanes. So chemical reactivity. First thing is the chemical reactivity. So we know that whenever we react halogen alkane, basically the functional group is carbon bonded with halogen. So the carbon atom bonded with halogen, that bond has CX bond has to be broken. As this bond has to be broken, so the reactivity depends on its strength. So you know that when you go down the row, fluorine is the smallest atom, then chlorine is bigger, bromine is bigger, and iodine is the biggest. Astatine is of course even larger, but we are not including it into our course, so we are not discussing it. So going from top to bottom, from fluorine to iodine, the size of the halogen atom increases. Due to that, the bond length between CX bond length increases, and due to increase in bond length, their bond energy decreases. And we know that the lower the bond energy, longer the bond, it is easier to break. And when it is easier to break, it has a greater reactivity. So if you have uh, four halogenoalkanes, fluoroethane, bromoethane, chloroethane, and iodoethane. So the most reactive will be iodoethane because of the Ci bond is the weakest and the longest, and the least reactive will be CF, fluoropropane or fluoroethane, due to CF bond being the strongest and the shortest. So we will see that iodoalkanes will react immediately without any conditions, and fluoroalkanes will need a lot of energy and lot of catalyst and etc. conditions are required. So that's why you see the reactivity that is increasing down the road. So if the first reaction that we'll study about halogenoalkanes is nucleophilic substitution reaction. Nucleophilic substitution reaction. What is a nucleophile? We have studied earlier in the topic of introduction to organic chemistry that nucleophile is a species which is attracted to positively charged carbon atoms in the other molecule due to the presence of a lone pair of electrons. They may be charged or they may not be charged, but they have nucleophiles have a lone pair, and due to the lone pair of electron, they are readily able to donate that lone pair to a positively charged species. So they are very easily attracted to an electrophile, and having a lone pair of electron, they can easily attack on a partially positive carbon or to form the bonds with them. So you see there are examples of nucleophiles. Hydroxide ion is a nucleophile. Cyanide ion has a nucleophile due to the lone pair on carbon atom. Then water is a nucleophile, but it is a molecule, it's not an ion, but it has partial charges and lone pair on oxygen. Ammonia is also a molecule, it's not an ion, but it has lone pair on nitrogen that can be donated. So you see all these four nucleophiles have a lone pair to donate. They may be charged or may not be charged. The charge will be negative, not positive always. Mechanism. This mechanism, you see that it is followed by primary halogeno alkanes. Primary halogeno alkanes undergo SN2. SN2, S stands for substitution, N stands for nucleophilic, and 2 stands for bimolecular. We call it bimolecular because when we see the reaction, the reaction depends on the rate of the reaction depends on the concentration of two species, two molecules. One is the primary halogeno alkane. Concentration affects the rate of the reaction, and second is the concentration of the incoming nucleophile. So both the incoming nucleophile and the primary haloalkane concentrations affects the rate because both of them are involved in a slow step. The species that are involved in a slow step of the reaction mechanism will affect the rate of the reaction. Any species that is not present in a slow step will not affect the rate of the reaction. So what is slow step and what is fast step? The slow step is the reaction in whose rate of reaction can be measured, and fast step is a reaction which occurs like a tick and like a click, and you cannot measure the rate of the reaction. So the slow step will involve primary halogeno alkane as well as the nucleophile, incoming nucleophile. So both their concentrations will affect the rate of the reaction. So how this reaction takes place, if you see that the primary halogeno alkanes have partial positive carbon and a partial negative halogen. When nucleophile tries to approach to the carbon atom, partially positive carbon atom attached to the halogen, it will approach from the other way around in such an orientation so that it does not have any repulsion. If it comes from the side of the where the halogen is substituted, halogen is placed, halogen is partial negative and nucleophile is negative as a lone pair, so they will repel. So the only possibility is to come from the other way around, just to ignore to reduce the repulsion. The nucleophile will attack from the other way, from the other side, from where the hydrogen atom is there. Hydrogen atoms are too small to cause any steric hindrance, so nucleophile can attack from that side where the hydrogen atom is there. So you know primary halogen alkanes have at least two hydrogen atoms, so it will attack from the side where the hydrogen atom is attached. So now the nucleophile attacks onto the partial positive carbon, but the halogen does not displace immediately, but it forms a positively charged intermediate. So this reaction is slow and we can measure the rate of the reaction. So therefore the Nu negative nucleophile that is attacking on the carbon, this species is included in the rate of the reaction in the slow step, and also the halogeno alkane is also included in the slow step to form an intermediate in which nucleophile is also attached to the carbon and bromine is also attached to the carbon, or the halogen is also attached to the carbon. But the nucleophile, when adjoins with the carbon atom, it makes the bond of CX to become even more weaker, and due to slight heat this bond will then break to release a halide ion. The halide ion is also a nucleophile, so one nucleophile has displaced a halide nucleophile. So in this way, this is called a nucleophilic substitution reaction. In this way, in primary halogeno alkane, it is a single step action involving an intermediate and forming the product. But when we go for tertiary halogeno alkanes, there is a big problem. The nucleophile wants to attack on the partial positively charged carbon attached with the halogen. The incoming nucleophile experiences lot of repulsion and steric hindrance. One side there is a partial negative halogen and all other sides are surrounded by alkyl groups. So the alkyl groups does not allow the nucleophile, incoming nucleophile, to attack onto the partial positive carbon, which is now in the center on the cage of the tertiary halogenoalkane. So what happens is that in tertiary halogenoalkane, the first step is nucleophile does not attack. Incoming nucleophile cannot attack. So what tertiary halogenoalkane do is it breaks the bond of CX first, and this bond breaking is a slow process. It's a slow process, so rate can be determined. In this way, when the rate is determined, the only concentration of tertiary halogenoalkane is involved, and the nucleophile attacking the halogenoalkane is not there. So that is why we call it as SN1, nucleophilic substitution unimolecular. So in unimolecular means only one molecule, that is tertiary halogenoalkane concentration, is affecting the rate of the reaction. When you have the reaction is complete in the first step, you have got carbocation intermediate and a halide nucleophile that has left. Now there is a path cleanly opened for the incoming nucleophile to attack on the carbon, which is now positively charged. So you know, when positive and negative charges attract, the reaction occurs like a click, and the reaction is too fast to occur, so the rate cannot be measured for this second step. So to form the final product in which the incoming nucleophile is now there, such as hydroxide ion to form alcohol, or nitrile to cyanide ion to form nitrile, or ammonia molecule to form amine. But the second step is fast, so its rate cannot be measured. That's why we can say that it is an SN1 mechanism, because only one molecule is involved in the rate determining step in a slow step. So SN1 is two-step mechanism, but only one molecule affects the rate, that is tertiary halogenoalkane. SN2 is a single-step mechanism with an intermediate, positively charged intermediate, but the reaction is having one step, so both the incoming nucleophile and the primary halogenoalkanes both affects the rate of the reaction in the slow step. So this is how SN1 and SN2 is there. So you say that what happens to the secondary alcohols, halogenoalkanes. So both SN1 and SN2 can be used. Mostly we use SN2 because it also has two halogens, two carbon atoms attached to the primary carbon. Therefore, it feels more steric hindrance. So now see that this is the mechanism shown. So if it is primary, you have got a partial positive carbon which is easily attacked by hydroxide ion to form an intermediate, and then intermediate changing to an alcohol. Cyanide ion, we have taken an example of tertiary in this case. So you see that a two steps mechanism. First step is slow and the second step is fast, and involving the formation of a partial positive intermediate to form a positively charged carbocation. And ammonia also goes away. Fate of nitrile is very important, because whenever you are handling a question of organic, you will be following reaction pathways. So when nitrile is formed, I've told you that one carbon is added. So the nitrile can even further be reacted to form new organic compounds. We have two or three reactions of nitrile that are required for our syllabus. One is acid hydrolysis, means again reaction with water, but in the presence of hydrochloric acid, hydrogen ion is there. When you will hydrolyze nitrile with acid, you will got carboxylic acid. So Cn changes to COH and N changes to ammonium ion. Ammonia is formed, but due to the presence of acid hydrogen ions, ammonia changes to ammonium ion. So acid hydrolysis will change nitrile to carboxylic acid. So if you start from 2-bromopropane and then you react it with cyanide in ethanolic condition, you will get uh, a nitrile with one carbon extra, and when you hydrolyze that nitrile, you will get a carboxylic acid with one carbon more. So starting from butane, you will go to pentane. If you start from ethane, you will go to propane, propanoic acid. So carboxylic acid is formed when you hydrolyze in the presence of an acid. Second is alkaline hydrolysis. It is also the same way. CN bond changes to COH and N changes to ammonia. But as you are using alkaline condition, carboxylic acid that will form will react with the NaOH to form salt and water. So you get RCOONA, sodium salt of carboxylic acid, not the just acid. Ammonia is there is no ammonium ion because there is no hydrogen ion to form ammonium, and water will be formed. Third reaction is reduction. So nitriles can be reduced using either of the two reagents, lithium aluminium hydride. The complete name is tetrahydrido lithium aluminate in the presence of dry ether, or aqueous alkaline NaBH4. So it is sodium tetrahydroborate. The nitrile will be reduced. C triple bond N will change to double bond, and then double bond to single bond, and keep on adding hydrogen. It's a sort of addition of hydrogen to form RCH2NH2. So amine is formed. This reaction is not similar to the reaction of ammonia with halogen alkane, because in that case there is no carbon extra added to the carbon chain. But when you have reacted the halogen alkane with cyanide and you form a nitrile and then you reduce it to amine, you will have one more carbon atom in the carbon chain. So amine with one more carbon atom than the halogen alkane from which it is formed is there. So we will react the halogen alkane with ethanolic NaOH or KOH. When you react ethanolic NaOH, not aqueous NaOH, this will cause elimination of halogen from one carbon and hydrogen from the next carbon, the immediately next carbon, to form an alkene. So elimination can be done using ethanolic KOH or NaOH. If you use aqueous NaOH, you will get alcohol. But if you react halogenalkane with ethanolic NaOH or ethanolic KOH, you will get a corresponding alkene. And the rule of forming alkene is that the carbon atom from which halogen is removed, the hydrogen atom is removed from adjacent carbon atom, neighboring carbon atom, adjacent carbon atom. So the double bond is formed, and we also called elimination reaction as dehydrohalogenation, because you remove hydrogen and halogen. From one carbon you remove halogen, and from the immediate next carbon you remove hydrogen to form an alkene. So the reaction is quite important. If you have aqueous NaOH, you will get alcohol. That will be a substitution reaction. But if you have ethanolic NaOH, you will get an alkene. That is called elimination. Finally, some properties of CFCs. They are chemically inert, they are non-flammable, they have low toxicity, and therefore if you release them in the atmosphere, they do not cause any harm to us. They are volatile, and they can be used as solvents. The uses of CFCs, you know that they were plentiful used in making in refrigerant gases and aerosols. They were also used to cause air blowing, to blow the plastics to form spongy material, and they were also used as fire retardants. CFCs have a very harmful effect. Chlorofluorocarbons have caused ozone depletion, and due to that we are now exposed to ultraviolet radiations from the sun, because you know that ozone blocks UV rays. UV rays causes skin cancer, cataracts, the disease of the eye, and it is quite harmful for us. It can cause us cancer. So, but we have ruined it by throwing lot of CFC into the upper atmosphere and causing the CFC to deplete. How CFC depletes the ozone? You can see this reaction. When CFC is exposed to UV rays, it is stable in our atmosphere. The temperature or the radiations present in our atmosphere does not affect the CCl bond or CF bond of CFCs. So if you see this diagram, we have an example of CFCl3. CF bond is small, so usually does not break even in ultraviolet radiations. But CCl bond is long and is weak and can be broken in the presence of UV light. UV light has sufficient energy to break that bond. So when that bond is broken, this bond is broken by, we know that, a homolytic fission to form chlorine free radical. So the chlorine free radical will then attack ozone molecule, O3 molecule, and takes one oxygen from ozone to form oxygen molecule. Now you see, oxygen cannot stop UV rays, ozone can do that. So the problem further is that this reaction does not stop here, but it carries on as a catalytic activity, and ClO, when it is reacted with another ozone, it forms a oxygen molecule and Cl free radical is formed. So Cl free radical is acting as a catalyst. It will attack another ozone now. So if you see the third diagram, in the second column, the Cl atom is now free. So that is why one molecule of CFC can release one chlorine atom, suppose one chlorine free radical, and that one chlorine free radical can be catastrophic. It can be too harmful because it keeps on attacking the ozone molecules and breaking them down into oxygen molecule, and then attacking the next molecule of ozone and the next molecule of ozone, because this is a catalytic activity. So it was very harmful. What are the possible solutions? We have replaced CFCs with hydrofluorocarbons. Hydrofluorocarbons and have no Cl bond, or if it has only one CCl bond, and it is Cl is replaced by hydrogen. So that is how we can reduce CFCs like this. So how can we protect our atmosphere from the ozone layer from CFCs? One is to reduce the use of CFCs and use alternate CF aerosols such as HCFs, hydrofluorocarbon (HFCs), or you collect and recycle CFCs and do not allow it to escape. This is quite difficult because when ACs gases big leak or fridge gases release, we cannot collect them and find alternatives. We have found some alternatives, but there is some problems with HCFCs because they are quite reactive, and they have caused they can be easily flammable. They are easily flammable, and they are toxic as well. So that's why using them is quite harmful. We can use LPGs, we can use blowing agents, air blowing agents instead of using aerosols, and you can use water-based cleaning systems for electronic industries instead of using halogen alkanes. So I hope you've got some clear understanding of halogen alkanes, their properties, their structure, and the reactions that has involved. So thank you very much, and we'll meet